All right, day 14 notes, part 2. So we're going to start with the sum identity of cosine and sine, and we know, going back to what we learned previously in pre-calculus, cosine sum is cosine A cosine B minus sine A sine B, and the sine of a sum is sine A cosine B plus cosine A sine B. So we're going to use these to help us find some derivatives. So we're going to find the derivative of sine and cosine. We're going to use the difference quotient. So the first thing I do is let's set each up. So sine of x plus h minus sine of x all over h as h approaches 0, and cosine of x plus h minus cosine x all over h. This is where the sum identities come into play. Okay, and now as we look over here, we get sine x cosine h plus cosine x sine h, and then the minus sine x all over h. I circled these because hopefully you notice, hey, I have a sine x in each of those, so I have a common factor that I can take out. Over here I get cosine x cosine h minus sine x sine h minus cosine x. Once again, I circled where I have like term and I can factor out a cosine x. We're going to do that right now. Okay, so step one for each of these, I just rewrote it so where I could get the like factors right next to each other. And now what I'm going to do is on the left side, let's factor out a sine x, and I'm left with cosine h minus 1 plus cosine x sine h all over h. Over here I factor out cosine x from these first two terms. And I should see, hey, I'm kind of have the same thing. And hopefully you can start to visualize that we're going to get some of those special trig identities that we talked about earlier. So let's separate these into each into two fractions. Okay, so now that I have them as two separate fractions, I should start to visualize, hey, this is pretty important. That was one of our special trig identities. And this was one of our special trig identities. And then over here, get the same thing on each of those fractions. So let's direct substitute and see what we get. So over here, as h approaches 0, this cosine h minus 1 over h is equal to 0, and sine h over h equals 1. So sine x times 0 is 0, and then cosine x times 1 is cosine x. So the derivative of sine x is cosine x. And over here, the limit as h approaches 0 of cosine h minus 1 over h is 0, so I have cosine x times 0, 0. And then as h approaches 0 of sine h over h, we knew that was 1. So I get negative sine x. So the derivative of cosine x equals negative sine x. And down bottom on the notes, this is what we get. So ddx of sine x, which is saying take the derivative of sine x, that equals cosine x. ddx of cosine x, which again means take the derivative of cosine x, and we get negative sine x. All right, these next four examples ask us to find the equation of the tangent line to the graph of the function at the given point. All right, what do I need to do? To take the derivative, which will give me the slope of the tangent line, I first need to simplify anything. So we're going to have to do that in the first one. I need to know the point of tangency. Well, that's just substituting in what I know here. For example, x equals negative 1. I substitute that into the original function, so I'll get the point of tangency. Slope of tangency I get by substituting in this value into the derivative, because the derivative represents what the slope of the tangent line is. And then once I know a point and a slope, I can use the point-slope form of an equation of a line and find the equation. So let's do these. All right, so the first one, I took x plus 1 and squared it, so that's binomial being squared. Yeah, x squared plus 2x plus 1. Now we use the distributive property, distribute the 2x to each of these three terms, get those, take the negative 1, distribute it, and then combine like terms. So now from here, I can then take the derivative, and my power rule says 3 times 2 is 6. Decrease the exponent by 1. 2 times 3 is 6. Decrease the exponent by 1. This is really understood as negative 1 x to 0, 0 times negative 1, 0, 0 times anything. And we learned the derivative of a constant is 0. So let's find the point of tangency by substituting into the original function. What do we have? Negative 1. That's going to give me my point of tangency. And the slope of the tangent line is substituting in the -1 into the derivative. So let's do that. So when I substitute these in, we get 0 for each of those. So now, and this represents our point when x is -1, y is 0. So let's do that. My equation ends up being y minus 0 equals 0 times x plus 1. And hey, that 0 times everything. I could leave it like that, but we end up finding out, hey, we get y equals 0. And hopefully see that that's the x-axis. So that is the tangent line at -1 of that cubic function up above. All right, let's do the same thing for second one. And we're looking when theta is equal to pi over 2. So I don't need to simplify this, so we're just going to take the derivative and we treat theta like x. So the derivative of f, or f prime theta, it's going to end up being, so there's 4, and then what's the derivative of sine? That is cosine, so we get 4 cosine theta. And if I took the derivative of x, it'd just be 1. That's like x to the first, but that's going to be -1. Okay, same idea. I have to find the point of tangency. How do I do that? That's just substituting in, and I should be doing pi over 2. And same thing for the slope of the tangent line. That is substituting into the derivative pi over 2. Let's do that right now. Okay, so when I substitute in pi over 2, 4 times sine pi over 2, sine of pi over 2 is 1. So that's 4 minus pi over 2. I'm just going to leave it like that. And then the derivative is 4 cosine pi over 2. Cosine of 90 is 0. So it's 0 minus 1, -1. So now I can come up with my equation of the line. Again, y minus y1 equals m times x minus x1. Looks like this. I can simplify it, and we get y equals -x plus 4. But we can always leave it in point slope form. All right, let's do these last two. So we find the point of tangency by substituting back into the original function. We get 2 pi minus 3 for that y value, so it's the point of tangency pi, 2 pi minus 3. For the slope of the tangency, we substitute back into the derivative, and we just get 2. So let's use our point slope form equation of a line, and we get, so we can leave it like this, or you could simplify. In this case, some things will cancel out. We get y equals 2x minus 3. All right, I'm going to do the last one out. Just pay attention to the fact that when that radical, we're going to write it as a rational exponent. Square root is 2, so the square root of x cubed is the same as x to the 3/2 power. Okay? So just follow along, and then we'll answer those last few questions, and then we'll go over these and work on the homework. So we get the derivative. Again, we have to work with our exponents here, rational exponents. So we get the derivative is -1 all over the square root of x cubed. All right, and here's what we get. And we're just going to leave them in these unsimplified versions. So the point of tangency is 2 and 4 over square root of 8, and the slope of the tangency is -1 square root of 8. So for our equation of a line, y minus y1, so that's y minus 4 over square root of 8 equals the slope, -1 over square root of 8 times x minus 2. And for what we're doing right now, that's all we need to get to. Okay, and let's answer these last few questions. Okay, the first question, given the equation of a function, how might you determine the value at which the function has a horizontal tangent? Explain your reasoning. We know a horizontal tangent occurs whenever you have a max or a min, so when you're changing from either increasing to decreasing or decreasing to increasing. And when does that occur? That occurs when the derivative equals 0. So if you're given the function, take the derivative, set it equal to 0. So let's do that on this next problem. So the first thing we do here is take the derivative. We get 3x squared plus 1. Then we take that, set it equal to 0. Subtract 1 from each side, divide both sides by 3. Take the square root of both sides, and we get plus or minus the square root of -1/3. Well, you can't take the square root of a negative, so there's no solution. And now since the derivative never equals 0 at any value of x, then the original function never has a horizontal tangent. For the last one, we want to do the same thing. So the derivative is 1 plus cosine theta. Now we're going to set that equal to 0. And now we're going to solve. And we get theta is where the inverse cosine is -1. There's an infinite number of answers, but they say on the interval from 0 to 2 pi, not including 2 pi. So we find out theta is just pi, because obviously it could go around the circle an infinite number of times. Okay, so we'll take a look at some homework next class.